The standard reaction is we're taking an allylic group, reacting that with a reagent, NBS. Usually they do some type of non-halogenated solvent, something that's not going to react. And then we can react that with usually light. Sometimes they'll have it or heat. Okay, so NBS will work with either light or heat. And we get allylic hydrohalogenation, or we got we get allylic halogenation. So NBS is N-bromosuccinimide. The reason we use the NBS is that if we had taken this reagent and react it with Br2 and Cl4 with light, well, have we seen this reaction before? Yes, this is just the halogenation of an alkene, right? So we can't just add bromine and light to an alkene like this to get the bromination. So what we need to do is add something that will supply a bromine, but not react in the way that Br2 will. So that's the reason for the NBS. The other thing that we need to realize is that the radical the allylic radical is actually more stable, slightly more stable than the tertiary, which is more stable than the secondary, which is more stable than the primary radical, which of course is more stable than the methyl radical. So the stability follows that of an electron poor species, such as a carbocation. And in a carbocation, because of the hyperconjugation, the tertiary and the secondary allylic were about the same. Here, the allylic is more stable. So there's an energy difference between the two, substantial enough to be more selective. Right, so that's a few things that I need to know. First, we're using NBS because we can't add bromine. And then allylic is going to be the most stable. So what does the mechanism look like? Well, first we have initiation. So with light or heat, we can get the fishhook arrows, right? The little 1-barb arrows. Forms bromine radical. And that bromine radical can react with our again, the little half arrows, fishhook arrows. Now, at this point in the propagation, we've got to put in another process, which is now we form some HBr, right? Well, it turns out that the HBr helps decompose the N-bromosuccinimide back to just succinimide and gives us Br2, right? So once we formed a little bit of HBr, that trace amount of HBr starts to react with the NBS to give us trace amounts of Br2. Okay, not high concentrations, but small amounts of Br2. That allows us to give a second step of the propagation that does what we want with propagation, which is a cyclic process. So initiation, we form a radical. Propagation, we start to use that radical. Okay. The caveat here is that we need a Br2 so that we can get a cyclic propagation. That actually comes from the reaction of HBr, of the Br radical with the allylic position. I think that's HBr. HBr decomposes the succinimide to give us Br2. Okay, so that's occurring in the reaction. That Br2 gives us the second step. And one of the big parts that you need to understand about reaction mechanisms is ignition, propagation, and then termination. And again, termination from Thursday is any two radicals coming together to bond and eliminate those radicals. So in this case, it could have been two bromines. They'd be in low concentration, so not going to happen very often, but you could have had two bromines coming together. We could have the carbon radicals coming together to react with each other. Again, termination, any two radicals. That's why it's sometimes better to think about it as just elimination of radicals than to think about all the possibilities. Any of these could be the termination step. So these are very selective. They add one bromine to the allylic position. You can also use them for benzylic positions. So if we have a benzene, so similar stability. That's the allylic position. So this would be a benzylic position. Again, we get next to the benzene, the benzylic position is favored. These are high high yield reactions. So with halogenation, again, remember we get multiple products and sometimes they can get pretty messy because you can extract different protons. In allylic and benzylic bromination, they're pretty straightforward. You can get yields above 97% on a consistent basis of just one product. Questions about this one? Yeah, and so yeah, the H nu is light energy. Again, we can use light. Radical reactions work well with light energy. A few of them work well with heat. So whenever you see the H nu, that's just light. Radical hydroboration, not hydroboration, hydrohalogenation. Addition. So if we do an addition reaction with a hydrogen bromide and add hydrogen peroxide, we can get the anti-Markovnikov bromination. Remember that if we did this reaction without the hydrogen peroxide, we would have gotten a Markovnikov product. So this is from the addition of alkenes. This was an electrophilic reaction, right? And this one up here is a radical reaction. So the addition of the hydrogen peroxide converts this to a radical reaction. Now with this one, you'll see heat very often, but it's not standard. You don't see heat all the time. So the lack of showing heat in the reagents for this one doesn't mean that the reaction is not occurring. Okay, hydrogen peroxide will start to degrade even at room temperature. If you've ever used hydrogen peroxide to clean a cut, it'll degrade as soon as it comes in contact with blood. So it's pretty fast to degrade. So you sometimes will see heat here as well, a little delta H, but if you don't see it, that doesn't mean that it's not going to react. Okay? So what does the mechanism look like here? So again, we start with initiation when we're looking at radical reactions. So we get half-barbed arrows. Okay. That's gets a homolytic cleavage to give us the radical reactions. Then that radical reactant, the hydroxide reactant, reacts with the HBr. Okay, so we got two steps in our initiation here. So half-barbed arrows, we abstract that proton. That forms water plus our reactive radical, the bromide radical. Okay. Next step is propagation. So the Br radical will be formed, is going to react, and let me use the same reagent, but I'll turn it around. Okay. Now again, remember the reactivity or the stability of our radicals. So which is more stable, a primary radical or a secondary radical? Okay. Secondary radical, right? So it follows the same type of stability that we see with carbocations. So secondary radical is going to be more stable. So when the bromine reacts with the alkene, right? Notice what's adding first. What's adding first is the bromine. That means that I add the bromine radically to make the most stable radical. So I've added the bromine to form the secondary radical. Then that radical, to finish out the propagation step, reacts with HBr to reform our reactive radical, the bromine, and to complete the reaction, right? The anti-Markovnikov addition of the hydrogen and the bromine. And then what happens in termination? Any two radicals come together, so we could have two bromine radicals finding each other. Right, that's a termination. We could have had two hydroxide radicals coming together. Could have had the carbon radicals, let's say, plus a bromine radical. This would be incredibly rare, but you could potentially end up with a trace of this. So again, termination, students often have problems with termination radical reactions because they're not standard. If you study your initiation and your propagation for each of these reactions, they always give you the same initiation and propagation. Termination, on an exam, I can pick any two radicals that would have been present in that reaction, have those two radicals react with each other, and that's the termination step. So there's lots of possibilities for termination steps. Don't let that throw you, just watch. In initiation, you're forming a radical, right? In propagation, you're using a radical. So you start with a radical, you end up with a radical. And termination, you go from two radicals to no radicals, right? You're terminating the radicals. Okay. Okay, questions about the anti-Markovnikov addition of HBr. HCl will work as well. Hydrogen fluoride doesn't work as well. Hydrogen bromiide can work. You don't see it as often. The radical of the iodine is so stable that it's not very reactive. So most of your radical reactions are really going to be around bromine and chlorine. Okay, when we look at selectivity, we have a few things to consider. One is if we look at something like this, I could abstract the middle hydrogen out of that tertiary position, or I could have abstracted one of the primary positions, right? So, but monochlorination, monohalogenation here gives us two possible products. If we look at just statistics, right, there's only one possible hydrogen that I can extract from the tertiary position in the middle, but there's actually 9 that I could extract from the primary position. So if there was no selectivity for the halide, I would expect 1 to 9 if at the same time there was no selectivity between the primary, secondary, and tertiary. Right? So if there was no selectivity in either the alkyl position or the halide, then this is what I would expect. But we know that the allylic position, right, is more stable than the tertiary radical, which is more stable than secondary, which is more stable than primary. That sets up the first selectivity, which is our substrate. There's an energy difference in abstracting these hydrogens. So we have that selectivity. But we also have the selectivity between chlorine and bromine. The chlorine radical is a higher energy radical than the bromine radical. Between those two, right, the chlorine radical and the bromine radical, whenever we have a high energy species, it's going to be less selective. Right, because it has enough energy to react with anything it wants to react with. Whenever we have a lower energy species, a lower energy reaction, we have a more selective. So if we look at this reaction again, and we did this with chlorine, we see a distribution about 65 to 35. We do the same reaction with the bromide. Now this is a tertiary to a primary position. We see a substantial difference. So when we see chlorine, we're going to see distributions across all of the possibilities, right? We're going to see primary, we're going to see tertiary. With bromination, radical bromination with bromine, we're going to see high selectivity. So if there's a tertiary position, that's going to be all of your product. Anything else is going to be a minor product, a very minor product. In this case, right, trace, because we're going from tertiary to secondary. So if we think about allylic, right, chlorination with a allylic, we're going to get possibly some other products. Allylic bromination, we're only going to get the allylic product, right? So when we're looking at these two, the thing to take away from this is that chlorine will give you multiple products in decent yields, right? Distributions that are measurable. When you get to bromination, a primary to secondary, yeah, we might get a small difference there, but it would still be like 80-20%, even if the R factor is pretty low. But if we look at tertiary allylic with brominations, we're only going to get one product. Now, if you read on this, there are some calculations to get this determined. We're not going to worry about those. If you become a graduate student in organic chemistry, you'll learn those calculations. They're pretty straightforward. You number the number of hydrogens, you count all your hydrogens, and then you multiply that by some factor. And that'll give you close to what the actual experimental value would be. It's nice, it's kind of fun. If we had plenty of time, we might do that. But the truth is, if it's bromination, you're going to get the most stable product. If it's chlorination, you're going to get a dysproteuthric product. That's what that calculation will tell you. Okay. Questions about radicals? All right. So again, if we go back to our learning outcomes, okay, we've covered right, the stability and structure of radicals. We've looked at radical halogenation, allylic bromination, and radical hydrobromine addition. We've looked at initiation propagation steps in several cases, and we've looked at the selectivity of the two, chlorine and bromine. Again, fluorine is such a high reactive species that it's not very useful. In fact, it can often just cause you explosions and small fires in the reactions. And iodine is so unreactive that it kind of sits there. It's a stable radical, and it's hard to get it to do much. Okay, so again, just think about the chlorine and bromine. So we've covered those. Okay, so we're going to start alcohols, ethers, and epoxides today. The first thing to do is look at preparation of alcohols, and we already know some of those. And the ones we know, right, have to do with our alkenes reaction. So if we take an alkene and react it with water and acid, right, we're going to get an alcohol. If we take an alkene and react it with hydroborane, followed by hydrogen peroxide and a basic workup, we're going to get an anti-Markovnikov alcohol. Again, these are reactions that you should be studying for the alkene step. We could also take an alkene, react it with mercury acetate in water, followed by sodium borohydride. Still gives Markovnikov, but with no rearrangement. So again, 3 different ways to use this. It's always good to think about any of these to specifically write out what your regioselectivity is, Markovnikov, anti-Markovnikov, and then if there's stereochemistry, right? So in the first one, it goes through a carbocation, no stereoselectivity. The second one, there is stereoselectivity, right? The hydrogen and the OH would add to the same side. So syn type of addition. And then the last, there can be, but it's really complex depending on what your conditions are. So we usually say there is no selectivity in the last one, at least at this level. When you get to grad school, we'll talk about the conditions and how you can force this one way or the other. Okay, so that's from alkenes, right, to alcohol. So again, if you look at learning outcomes, you need to be able to convert alkenes to alcohol. So think about all the ways you can do that. We also, right, learned that we can do a nucleophilic attack, right? So this is SN2 style process, right? We might have to worry a little bit about the elimination. Let me rewrite this. Okay. No rearrangement. So if we look at this one, right, we potentially could have elimination products here. If it's the primary, the substitution would be favored. So substitution elimination, sometimes in competition. If we looked at, a tertiary position with water, right, we could get solvolysis, and that would make an alcohol. Okay. So we have our alkene reactions. Yes, sir. Oh, sorry. I can't see that. Okay, so SN2, we could get alcohol formation. SN1, we could get alcohol formation, right? Slightly different reaction conditions. Heat, usually in SN1, is a good sign. Okay, so we already have some preparations of alcohols that you've learned so far. Okay, so we're going to see this, and you'll see this as you continue through the whole year, is that you're going to start to re-see things, right? So a reaction of an alkene then becomes a preparation of something else. And so again, that's why it's good when you're making up your flashcards to think of it both as reactions of an alkene and a preparation of an alcohol, and start learning them that way. So as you bring those classes, you'll see them both as reactions going forward and then production of something coming in. Okay, so we're going to make alcohols as reductions of carbonyls. So if we use a hydride donor, and your main two hydride donors, will add some to this as you go through the year. But your main two are sodium borohydride and lithium aluminum hydride. The hydride is going to act as a nucleophile. So generically, depending on no matter which hydride donor you're going to look at, and we'll talk about the subtle differences between the two and the reactivity differences between the two. But if we take a carbonyl and react that with a hydride donor, okay, this is generic. What's happening is our hydride is attacking the electrophilic position, right? That adds my hydrogen. And then my next step is going to be a proton transfer. To complete the reaction, to get the alcohol. So this is, whether it's sodium borohydride or lithium aluminum hydride, we both are getting a hydride electrophilic attack on the carbon of the carbonyl. So if we look at this specific one, so first step, we have the hydride attacking the carbonyl, lone pair goes up. This results in the BH3. We want to show her the counter ions, we could. We had the hydrogen. Now the hydrogen is going to add to one of the two planes, right? So this is a planar molecule, so we're going from sp2 to sp3. So therefore, there's no real stereoselectivity here because it can attack the either front face or the back face of this. So I show it going down, but it's actually either in the front face or the back face of this group. Okay. And then in this case, right, my solvent is my proton donor. So I had methanol as my solvent. That solvent's going to be there, and I will get, reaction with it to give me my proton transfer, to get me to my final product. We could have done the same reaction with lithium aluminum hydride, but we would have had to take a slightly different step. Okay, with lithium aluminum hydride, the lithium aluminum hydride will react with water. So if lithium aluminum hydride comes in contact with water, it ends up with aluminum hydroxide compound. Plus heat. Okay. So if we're producing hydrogen and heat, is this a reaction we want to be doing a lot? No. This one usually doesn't catch on fire, but it can catch on fire, right? Because I'm producing a flammable gas and I'm producing heat. So lithium aluminum hydride and water do not do a hydride reduction of the carbonyl. They just react with each other to give off hydrogen and some heat. So therefore, with lithium aluminum hydride, we don't put it in a protic solvent, right? So we can't put the lithium aluminum hydride in a protic solvent. So that's why we have a first step and a second step. That's one of the major differences between these groups, right? Is that sodium borohydride I can have in a protic solvent, usually an alcohol such as methanol or ethanol. But with lithium aluminum hydride, I have to have it in two different steps. I have to have my proton source for the second step in a second reagent. Okay. The result in ketones and aldehydes is the same, right? We get the reduction of the alcohol. Now I've shown it with ketones. Let's go ahead and show it with alcohol, aldehydes. So if I had done an aldehyde, something like sodium borohydride and ethanol, So with either aldehydes or ketones, we can use either sodium borohydride or lithium aluminum hydride to reduce the carbonyl to an alcohol. Questions about this one? With esters, okay, remember an ester is a carbonyl with a alkoxide group attached. So we have the oxygen carbonyl plus the oxygen carbon. We can reduce this to the alcohol. So let's look at the mechanism. Okay, so similar, the first step is nucleophile, the hydride, right? The nucleophile attacks the carbonyl. At this step, I have this tetrahedral with the oxygen negative. Now, when we had the ketone, if we go back up to the ketone process, right? At this point, I had the oxygen negative and I had 2 carbons and a hydrogen. Are any of those 3 good leaving groups? Meaning when they leave, will they be stable? Carbon negative, hydrogen negative, carbon negative? No. I mean, we can think about the hydrogen negative going back, but remember the hydrogen negative has, the hydrogen has a pKa of about 50, right? So it's very unstable. So forming a hydride is a hard job to start with. So therefore, when we look at this reaction, now though, when we look at it, I have carbon, hydrogen, and I have this methoxide. Is the methoxide a decent leaving group? Yes, right? We can see that leaving. Oxygen negative is not as stable as a halide leaving group or something else, but it is relatively stable. And what would the result of that leaving be? Well, an oxygen negative. Where am I right now? An oxygen negative, right? So I have a potentially decent leaving group that doesn't substantially change the stability of the total solution. Okay. So what I've recreated here, or what I've recreated here, is an aldehyde. Okay, so hydride attacks the ester. The hydrogen adds, right? The oxygen negative comes down, kicks off the methoxide, and now we have an aldehyde. Is an aldehyde reactive with a hydride donor? Yes, we just saw that, right? High aldehydes will react with either sodium borohydride or lithium hydride to reduce. So what happens here is that we get another reaction. And this time I'm going to put R, OR here. Now, the reason that I changed this a little bit is that we have aluminum, right? Aluminum is a electrophile. What would happen if I had my OCH3 and aluminum around? Not 4, but just 2. Well, what can happen, right, is we can use these two will react together, right, to regenerate the hydride donor. So therefore, whenever we look at the aluminum, it's not that we can only use one H, right? We could potentially use all 4 H's. Now, it turns out that reactivity of this is somewhere between 2.5 and 3.2 yield, meaning 4 hydrogens on there are going to react between 2.5 and 3.2. And it really depends on lots of things, including how good of a lithium aluminum hydride do you start with, how pure is it, what's your solvent, how wet is your solvent, so forth and so on. But this reaction, what that means is that this reaction, you don't have to show 2 equivalents of lithium aluminum hydride to get this reaction to occur, okay? That's the point I'm trying to get to, is even if you show just lithium aluminum hydride and they don't indicate how much is there, this reaction will go until it's complete. Sometimes you'll see them say 2 equivalents of lithium aluminum hydride, and that's fine. But the truth is, you've got it there, right? You have all the equivalents you need. Okay, so that's the end of the first step. So all of this, right, was step 1. Step 2 starts when I add in my proton source. And usually just a mild acid solution, just enough to be a proton source. And I get my final product. Okay, questions about this one? We can do a similar reaction. The mechanism is slightly more complex. So if I was going to ask you the hydride reduction of a carbonyl of a carboxylic acid derivative, I'd most likely ask you for esters. It's slightly less complex. The main steps are the same. There's a little hitch in the middle where you have to activate the OH group to be a leaving group. But let's put it this way, in the last 10 years, I haven't asked it. So let's say that we'll ask the ester if we get a mechanism for this one. So the process is more or less the same. The only difference is that we get a little bit of a modification here because we don't have the methexis, but we still have the hydride attack the carbonyl, and then the hydride attacking the aldehyde that's formed in the intermediate, and then the protonation. So these 2 steps are the same. It's this step that's slightly modified. The other thing we need to think about with these reactions, so hydride reductions, is if we look at a ketone, so let's just say sodium borohydride and methanol, and if we look at an aldehyde, let's say sodium borohydride and methanol, and again, it can be methanol or ethanol, no difference. And then when we go to these, right, we can't use sodium borohydride, so we have to use the lithium aluminum hydride. What do you notice about our products here? A ketone is going to result in what type of alcohol? Well, the ketone, right, already has 2 carbons attached, so it's always going to end up with a secondary alcohol. Could it ever form a tertiary alcohol? Not through hydride reduction. An aldehyde, right, so here's an aldehyde with either sodium borohydride or lithium aluminum hydride reduction. So a hydride reduction is always going to end up in a primary alcohol. An ester reduction with lithium aluminum hydride, remember sodium borohydride won't work, so we have to use lithium aluminum hydride. It's not reactive enough. It's going to give us a primary alcohol. So when we look at the hydride reductions, one of the other things to think about is if we were looking at a retrosynthesis, 3 of these could form a primary alcohol, but only one of them can form a secondary alcohol. So if you see a secondary alcohol through a hydride, we had to start at least with a ketone. The other 3 could be very similar, right? So we could have started with the ester or the acid or the aldehyde. They would have all given the same product. So Grignard reactions with carbonyls. Okay, so this reagent, when we have an R group with a magnesium and a bromide, that's known as a Grignard reagent. Grignard reagents are formed by the reaction of magnesium and ether. So they're not hard to form. When you get to the organic lab, you'll probably do a Grignard synthesis where you take a bromide, react it with magnesium and ether and form a Grignard reagent. The interesting thing about this process is that the Germans call it Umpelag, or some pronunciation close to that. If we look at this position, it's electrophilic, right? So that we've got a dipole moment going towards the bromine, making that electrophilic. But whenever I get the insertion, and this is an insertion of the magnesium between the carbon and bromine, what happens now is if we look at it, that's a magnesium, right? That's a metal. Metals are not electronegative, they're electropositive. So I actually see electron density going the other way. This becomes a nucleophile. So Grignard reagents are nucleophile. So I can take an electrophilic halide and turn it into a nucleophilic Grignard reagent. So if we look at the mechanism at the top, it's a pretty straightforward mechanism, thinking about that carbon as a nucleophile. So starting with the ketone, Grignard reagents are usually shown bonded, not as positive and negatives. So there is enough dipole in that polarity in that bond so that it's not a ionic, but a covalent bond. So the nucleophilic carbon attacks the electrophilic position. That forms the oxygen negative. And then I have my salt, all right, usually not shown, but we'll show it here. So first we get the nucleophilic attack. So that's step one, or reaction one. Reaction two is then adding the proton source. And we can't have the magnesium, right? This is a nucleophilic carbon. What would happen if we had a protonic solvent? Well, the nucleophilic carbon would freak out the proton and become an alkane. So therefore we have to separate it. So like with lithium monohydride, we have to separate the two reagents, right? We have to do the Grignard reaction, then add our proton source. So first step, second step. And then we get our alcohol. Okay. Questions about this mechanism? Similarly, we could take an aldehyde, such as benzaldehyde, react that with an ethyl Grignard reagent. Okay, so not only is this creating an alcohol, it's also doing one other very important thing. What's it doing to our carbon skeleton? It's extending our carbon skeleton, right? So up to this point, the only thing that really did that was the acetylide reaction. So acetylide reacting with an electrophilic carbon could add two more carbons, right? And then we could convert the alkyne into something else. Here, we're starting with a carbonyl and we're adding carbons, right? And the Grignard, we can add as many carbons as we can form the Grignard. And so as long as you have a decent alkyl halide, you can form that Grignard. Tertiary Grignard is a little bit tough to form, but primaries and secondaries work fine. And tertiaries will work, just a little bit messy in the lab. Doesn't mean it's not possible. Okay. So that's one of the other things to think about the Grignard reagent is that we are adding carbons. So aldehydes and ketones, to do this pretty straightforward. We can also do this with esters. Here we are going to put two equivalents. So in the first step, right, Nucleophilic carbon attacks the electrophile. The leaving group, which is the pi bond, leaves. That forms the oxygen negative. I now have a bond between my carbonyl carbon and my Grignard carbon. Now I've got an oxygen negative. I have a decent leaving group, right, with the methoxide. Not great, but decent. That reforms my carbonyl. Okay, and the reason that we see two equivalents on this most often is that the ketone is actually slightly more reactive than the ester. So it's difficult to do only one of these and stop in a clean process. So then here, second equivalent, nucleophile attacks electrophile, leaving group leaves, right? So my nucleophile, my carbon negative, attacks my electrophilic carbonyl, pi bond is my leaving group. So I have the oxygen negative. And then second step, we add in our proton source. So we get a proton transfer. Oxygen negative picks up the proton. This is all first step, and then this is second step. Second step is the protonation. So ketones and aldehydes, we get one addition of the Grignard. In esters, we get two additions of the Grignard. Questions about this one? So again, looking at these reactions, if I take a ketone, react it with a Grignard, I'll get an alcohol. Take an aldehyde, react it with a Grignard. I'll get an alcohol. If I take an ester with two equivalents, I'll get an alcohol. Okay. And if we look at these and break it down a little bit more, right, this one is going to be a tertiary alcohol. So if we start with an ketone and we end up with a tertiary alcohol, then that can separate whether we're going to use the sodium borohydride or lithium aluminum hydride addition versus a Grignard. If it's going from a ketone to a tertiary alcohol, we had to use a Grignard. Aldehydes, we're going to end up with secondary alcohols. Esters, we're going to end up with tertiary alcohols. And the other caveat for an ester, right, is that whatever this Grignard was, I added it twice. So two of my R groups on my alcohol are going to be identical. Okay, so if you're doing a retrosynthesis and you notice two ethyls or two propyls, two methyls, right, that could have come from an ester. We got a few more minutes, so let me put a couple of here. I'll give you the reaction and the substrate and the reactant, and you tell me what the product is. we pushed the exam 1 and exam 2. I'm not planning to push exam 3 back because pushing exam 3 back would put it the Tuesday before Thanksgiving. And although I've done that in the past, I think that's somewhat unkind this semester. So we will keep exam 3 where it's scheduled. Right. Okay, let's look at the answers here. So the first one, we've got a hydroboration oxidation of an alkene. That gives me a anti-Markovnikov alcohol. Right, that's from your alkenes. You saw that a couple of weeks ago. Second one, we look at reduction of a carboxylic acid with lithium aluminum hydride. That's going to go all the way to the primary alcohol. Then the third one, we have an aldehyde reacting with a Grignard reagent. That'll end up with a secondary alcohol and adding 2 carbons. And again, it's always good to count your carbons when you're doing these, especially on multiple choice tests. It's easy to put 1 less carbon or 1 more carbon as a distractor. Questions about these 3 reactions? Okay. All right, we're on